Hello, my name is Daniel Haacke. This is my CIS 452 course project. So the goal of this project was to create a neural net which could recognize handwritten digits without using TensorFlow or Keras. So a neural net is essentially a graph where layers of perceptrons make up the nodes, and the edges are formed between nodes of one layer to nodes in the following layer. And they consist of one input layer, which is like the pixels for an image, for example, a hidden layer, and an output layer, which will contain your prediction. So the perceptron is really what's doing all the work in a neural network. It's got inputs coming from all the perceptrons in the previous layer, each with its own corresponding weight, and their products are summed to get what we call the weighted sum. And of course, that also has a bias, which is part of it. And then that gets fed into G, which is an activation function of our choice, usually the sigmoid function, and then it has its own output. A very typical activation function is called the sigmoid function, which produces a nice continuous smooth range of values between 0 and 1 instead of just a hard 0, 1 to kind of help the network learn. So since the x input to the weighted sum equation is actually a vector containing activations from the previous layer, we can consider a generalized perceptron to take the vector g of L minus 1. So this is all the activations of the previous layer in vector form. So for any perceptron j at layer L, we can compute the individual weighted sum with this equation. And I'm going to try to neaten this up. So we're going to try to get rid of the biases by just kind of including it in the weight matrices. So we replace B with Wj0 equals B. We add a dummy activation, G0 equals 1. And then we can actually we can get rid of the bias and only consider the weight matrix for the current layer and the activation vector of the layer previous. And you'll notice that the indices Ji, they're actually in the reverse order. So Wji is the weight from perceptron I in layer L minus 1 to the perceptron J in layer L. So right here I've got one noted. This is perceptron 1 in layer L minus 1, perceptron 2 in layer L. So that's actually WL 2, 1 and not 1, 2. And the reason we do this is so we can make use of the matrix multiplication. So this dotted with that, right, is going to give you the weighted sum for that current layer. So W10 we said was the bias, G0 we had a dummy value of 1. So this Z1 value right here is just the bias, and then everything else in this vector is coming from this part right here. And the reason we do that is because now we have the weighted sum in vector form very nice and neatly defined as the weight matrix for that layer dotted with the activation vector of the previous layer. So what we do is we continue to propagate these activations forward. So to do so, we want a nice neat way of writing our activation vector as well, the same way we wrote our weighted sum vector. And so that is just whatever activation function you have, and then you just put in the whole vector as an input. And the beautiful thing about the NumPy library in Python is it will compute each element, the function of that element for you. So you get your whole activation vector just by plugging this into your activation function. And then you propagate this all the way to the end until you get to your output layer, which will then contain your predictions. So here's the algorithm written out. So your very first G vector is actually just going to be like the pixels of your image, for example, right? So G1 is equal to X. Then for every single other layer, you just say, okay, the current vector is going to be the activation function of the weights dotted with the activations of the previous one. And you continue that until you get to your final activations of your final output layer, which are going to be your predictions. So every neural network needs a loss function or error function, because when you get to the end, obviously you're not going to do well, especially initially, because the weights are randomly initialized and you're just going to have a bunch of garbage values. But you know what you should have because we have the expected values. So a typical loss function here is we can use like this: the cost is equal to 1/2 of the sum of the difference of what the prediction was compared to what we expect it to be squared, right? So you take all these and you sum them up, you square them. That is your loss function. And the goal here is to minimize the loss function. So we can do this by using a method called gradient descent, which is going to help us find the derivative of the cost with respect to each weight. And there's a lot of math that's going to go on in the next few slides. I'm just going to kind of skip through it. You can look up the derivations yourself, but basically we use the chain rule of calculus and get a bunch of partial derivatives. And we back propagate these partial derivatives through the network going backwards, and we keep getting these little delta errors throughout as we go on. And the errors that we find at one layer are actually used to then further calculate the errors at the previous layer. And once you've taken that all the way back to the very beginning of the network, then you've got the derivative of the recost with respect to each weight. You can update each weight to their new value using this function here, or this one is the same, just another way of writing it. And this variable right here is your learning rate, right? This is the previous value of the weight, and then this is kind of the partial derivative stuff that we have figured out. And then you're done, at least for that part. You've updated the weights, and now your network should perform a little better. However, a considerable problem for the aforementioned algorithm is how slowly it learns. And this is because, as is, it must iterate through all the training examples before it updates the weights even a single time. A resolution to this is to learn a little bit at a time. And so this is performed by shuffling the training data, taking small batches, and performing the algorithm as if they were the only training examples, and then updating all the weights, and then continuing to the next iteration of training examples at one batch at a time. And then that's called one epoch of training. And then for stochastic gradient descent, you usually have many epochs, and you just do this over and over. And once you feel your network has been sufficiently trained, you can evaluate it to see how much of the test data it is able to accurately predict. So I took advantage of what's called the MNIST dataset, which is just a large dataset of handwritten digits and their expected values. And I only train my network on like 1 to 2,000 at a time, as opposed to all 60,000 for the sake of time, because it would take a million years. So my results aren't as good as the true scope of this network could be, because I did not do all the examples. But here's just some sample results. So I used a learning rate of 3, a sample size of 1,000, and a batch size of 10. And then here I did 10 epochs using the same data, and I got up to 73% accuracy. And then here 10 epochs of random data. So each time I did an epoch, it used random data. And you see I got a 5% increase here. And then here I did 20 epochs, and you see now it's getting really close. I've got 85.7% accuracy here. So it's getting there. And then this one I did like an even more thorough, higher batch size, and higher sample size with more epochs, and I got all the way up to 87%. So if I had actually used all the training data, I'd probably be in the 90s, but it takes too much time. Now, if you really want to make a good network that is good at image classification, you should be using a convolutional neural net. What I made was not a convolutional neural net, but more or less these have convolutional layers and pooling layers and repeats of such, and then they've got some sigmoid neurons. They have all sorts of stuff going on, and this is kind of like feature detection type of stuff. It's much more complicated, and I didn't really have time to do into it, but just keep in mind, if you really want to make a good image classification neural net, you should use a convolutional neural net. And here is just a brief look at some of the code that I used. All in all, there weren't really too many lines of code that I needed, because once you set everything up as vectors, it makes a lot of the math really easy to do in code. And the NumPy library handles a lot of like vector math and matrix math very well. So that is my talk. Thank you for listening. And if you want to learn more about the type of network that I built, I highly recommend taking a look at this website. And if you want a copy of this report or any of the code that I did, feel free to shoot me an email at my email address. Thank you.